Okay, welcome everyone. Thank you all for being here today. For our normal attendees, you may notice that I am not Michael. He unfortunately can't be with us this afternoon, but I will be emceeing instead. So thank you all for being here. We're very excited today to present to you a few talks from a number of very, very talented graduate students, and we hope you enjoy. So first up today is going to be Emily Bordeaux from Dartmouth College. They are going to be talking to us about stellar isochrone fitting with Fidanca. Emily, if you'd like to take it away.
Yeah, thank you so much, Catherine. Let me just get my slides pulled up here. There we go. Again, thank you. Like Catherine said, I'm going to be presenting a Python package called Fidanca, which is a toolkit for globular cluster science. I want to just point out quickly that this is not solely my work. I've been working with another student of my PhD advisor. My PhD advisor is Brian Chaboyer, and Fidanca has been developed in collaboration with another of his students, Martin Yang. There's a QR code here that you can scan to take you to the GitHub page if you're so inclined. This will also pop back up on the final slide of the talk. So because we're relatively limited in time, and I assume we're an astronomy audience here, I'm not going to dive into justifying why globular cluster science matters. Suffice it to say, there are laboratories for us. Instead, what I'm going to do is I'm going to talk about the kind of three pillars of what Fidanca is. It can do fiducial measurement, so measuring median ridge lines, measuring width of sequences, measuring multiple populations in globular clusters. Isochrone optimization, so looking at the distance modulus, the color excess, and the age of isochrones, and minimizing some objective function to get the best fitting of those three parameters. And then kind of as a side effect of its handling of isochrones, it turns out it's relatively straightforward then to take that and kind of transfer it into some relatively rudimentary but still useful population synthesis. So I'm going to go through each of these three pillars. And for each of them, I'm going to mention, perhaps some novel things that Fidanca is doing. Again, I'm not going to get too deep into the algorithmic complexity. Feel free to ask me any questions if there's a Q&A session later on, or send me a message at my email if you want. So for fiducial measurement, just to kind of motivate the problem here, this is a CMD of NGC 2808, Milky Way globular cluster, from Pietro et al. 2007. And what I've drawn here is these are just manually drawn little lines on here. I've drawn what we might call, the median ridge lines of two populations. So while globular clusters kind of canonically are single population, it turns out that, if you look at these things in depths with bands that have a pretty wide color throw, you see multiple populations in all Milky Way globular clusters that have been studied this way. And just to kind of take those lines away, if we look at the kind of the raw CMD, we're zoomed in on the main sequence turnoff here. You can visually pretty clearly see some high density regions and low density regions. And the idea here is we want to draw a line through these that we can then fit theoretical models to. It turns out to be kind of a non-trivial problem because of the large dynamic range and density variation from one part of the CMD to the other, and just because of relatively subtle variations that exist in parts of the CMD. The kind of the main novel thing that Fidanca is doing here is taking a convex hull-based adaptive binning approach where we keep the counting statistics in each bin the same, and then use the area of some convex hull that encompasses those points to define the number density of points at any given star. And this does a really effective job of really magnifying the high density regions and kind of dampening down the low density regions. There are some other things. There's some Bayesian modeling in there as well, but this is kind of the primary development here. This is all exposed through what we hope is a relatively simple API. It's installable as a regular Python package is, and we've got some pretty simple functions to use. So here's an example of how you might measure two fiducial lines in NGC 2808 and the F275 wide and F814 wide filters. And just to show you what the output of this might look like, these are lines fit with Fidanca. So you see it does a pretty good job of both identifying where the lines are kind of overlapping near the main sequence turnoff, and then where they kind of spread apart down further on the main sequence and up on the red giant branch. After we had fiducial line measurement, that leads directly into isochrone optimization, right? If we want to optimize the distance modulus, color excess, and age of an isochrone, we need those fiducial lines. The kind of primary novel thing I'm going to point out here is instead of looking at like a chi-squared difference between just the location and color magnitude space of the nearest points, we're using dynamic time warping, which is an algorithm that was originally developed for synchronizing audio signals. Really, here's like dynamic magnitude warping. Effectively, if you're familiar with isochrones, this lets us identify equivalent evolutionary points on the fiducial line in the isochrone, and then measure the distance between those equivalent evolutionary points. This gives us a slightly more curved objective function space, so it's a little bit easier to run an optimizer over that. Again, there's a pretty straightforward API, we hope, that's exposed, that lets you take in a fiducial line object from Fidanca and a MIST style isochrone and MIST style bolometric correction tables, and spit out, those 3 optimized parameters. Finally, population synthesis. I'm actually not going to show API examples here. The API for the population synthesis is still under construction. Though if you go to GitHub, you'll see some example code. Just note that will likely change the actual interface. But like you would expect from any like population synthesis code, it can measure completeness and uncertainties from artificial star tests if they're available. It can do binary population fraction modeling and mass function modeling. So the things that you would expect from a population synthesis suite. So I'm gonna wrap up there. I hope I took a reasonable amount of time. I know it's a pretty short talk here. I'll say thank you. I'm not sure if the Q&A session is right now or if it's after, but if there are questions, I'm happy to answer them.
Yeah, so normally what we do is if anyone has any real quick questions for Emily right now, we can take those, and then otherwise we can also circle back during the Q&A after all our speakers have gone. There is nothing in the chat at the moment, but let's see, I'm not seeing anything from the audience right now, so yeah. Perhaps we'll circle back in a moment. Thank you so much, Emily. So next up, we have Fergus Baker. Fergus is a PhD student at the University of Bristol, and he is going to talk to us today about general relativistic ray tracing with Gradus in Julia. So feel free to take it away.
Thank you very much. I'm going to apologize just before I start. I've had a bit of a cold the last few days and it's still sort of clearing up. So if my voice disappears, I'm very sorry about that. So hopefully you can, if I've shared the right screen, no, oops. One moment. Right, can you see that?
It's taking a second to load for me right now.
Yeah,
Okay.
I don't see it yet. It says, let's see.
Right,
Yeah.
give me just a second. That's strange, it's working just now.
Yeah, it was working a moment ago.
So share. Is it coming
There
up
you
now?
There it is.
That's good.
All right, brilliant, cool. So yeah, thank you for having me. My name's Fergus. I'm from the University of Bristol, and I'm going to be talking about Gradus.jl, which is the Julia package that I've been working on in collaboration with my supervisor, Andrew Young, for maybe the last year and a bit. So Gradus.jl is a general relativistic ray tracing toolkit, effectively. So hopefully you're a little bit familiar with what ray tracing is, and general relativistic ray tracing is in principle the same thing, except now light, instead of following straight line trajectories, the trajectory is distorted by the space-time curvature. So in this little animation, you can see there's the Kerr space-time. As the mass goes from 0 to 1, it starts introducing curvature into the photon trajectories. And as the spin A goes from 0 to 1, it starts introducing asymmetry into this picture too. And we can calculate the trajectory of the photons by through the geodesic equation, which is entirely determined by the metric, relying on the fact that null geodesics are the photon trajectories of a given space-time. So use cases for general relativistic ray tracing are imaging black holes, such as what the Event Horizon Telescope collaboration do. And the sort of 2 things that we're mainly interested in, which is spectral modeling and variability modeling, specifically in the context of X-ray astronomy, looking at how strong relativistic effects can, for example, blur different spectral lines from emission processes, or affect, for example, timing properties of different variability within accretion flow. And we use models of this nature in order to measure things like metric parameters, such as the mass and the spin, different parameters relating to the accretion flows and the disk parameters themselves, which we're using ultimately to test things like relativity and deviations from Einstein's theories. So why would you want to use Gradus over one of the other relativistic ray tracing codes? In my personal experience, other codes can often be quite brittle or were designed for a sort of single purpose to look at, whereas Gradus is really designed to be as general as possible and to simulate all sorts of different, wildly different models. Other code bases can often require a lot of familiarity to extend, or can also be quite tedious especially when we're wanting to add something like a new space-time, whereas Gradus is designed to really be extensible, as you'll see in a few slides. Furthermore, ray tracing can be quite difficult or even error prone, especially in some of the sort of higher order data products. Gradus overcomes or tries to sort of mitigate this by having a quite extensive test suite and continuous integration, so that we always make sure we agree with published or results in the literature already. And finally, speed and scalability. Gradus runs well on your personal laptop as it does on supercomputers without you having to change anything in your code. So our approach in achieving this is to use automatic differentiation to calculate the geodesic equation, which relates to the next point on symbolic computing too. We require only the specification of the metric in order to be able to calculate everything from there on in, whereas other codes, you would often have to do a lot of sort of manual mathematical work first in order to come up with a sort of simpler formulation or calculate the Christoffel symbols of your metric or whatever. But I won't dwell on that too much at the moment. Multiple dispatch, which is sort of like one of Julia's big selling points. So we can have really composable abstractions that recompile well and optimize well. And using Julia's heterogeneous parallelism, so that kernels written for the CPU can also be executed on other hardware devices, and we can benefit from like GPU acceleration quite straightforwardly. So to illustrate all of this, I'd like to run through what would otherwise be a really quite difficult example in other codes, which is to define a new metric, a new disk geometry, and a new coronal geometry, according to this little sort of toy comic in the slide, where you've got a sort of thin equatorial disk upon which is a sort of like thick slab corona, and then for simplicity using the Schwarzschild metric. So this is implemented by, first of all, just specifying what the parameters of your spacetime are. In this case, it's just the mass. You then define what the cutoff for the integration should be, which is the coordinate singularities, or in this case, the event horizon, which is at 2m. And then you can instantiate it with some arbitrary choice without loss of generality. The metric components, so Julia supports full UTF-8 character sets and binary operators too. So you can write it out pretty much as you would on paper. But you can go further than that. For sanity checks, you can then use things like symbolics and latexify in order to run through different parts of Gradus, including these metric components, using symbolic variables, and then print out the LaTeX code and render it to minimize the chance of making mistakes when typing out different mathematical equations. So adding disk models, in this case, we've got a slab disk that's parameterized by a height, a radius, and some emissivity coefficient. The emissivity coefficient is generally a function of position and frequency, but in this case, we're just going to keep it fixed at a constant value throughout the entirety of the slab cylinder. We instantiate it and then compose it using the circ operator with a thin disk in the equatorial plane that ranges from the innermost stable circular orbit of our spacetime out to 50 Rg in this case. We define the intersection criteria. So basically at every point along the geodesic, so it's tracing, it's just checking to see whether it's within the disk, plus some tolerance parameter to make sure that the root finder that we're using to calculate the exact point of intersection actually finds the exact point of intersection. The coronal model is specified in a similar way, in this case parameterized by the height and radius, which we take directly from the slab, from the disk slab. For this, we define a function that samples different positions and velocities within the coronal model. So this is all a bit of a mess, but effectively it's just a random point within the cylinder translated to spherical coordinates, and then just taking the equivalent circular orbit at that radius in order to calculate the velocity. And that's kind of it. After that, you specify where your observer is located in spherical coordinates at some sort of inclination. In this case, we've got a point function that's just coloring the pixels according to the redshift multiplied by some, so in the orcs in this case is the intensity from the radiative transfer. So here's an image rendered using render geodesics that just shows what the disk looks like with the relativistic warping. So you see the sort of stretching of the disk at the back and the false image here in the gap in the middle. You can also calculate things like how the coronal model that you've got illuminates the disk and the emissivity profile thereof, which is binned in this case radially. So you can see also what the effects of the radiative transfer, so having that emissivity being non-zero, are at large radii. You can also calculate even higher order products like line profiles or lag transfers, which are effectively like the spectra or the energy spectra and the energy of spectra over time as it arrives to the observer, which you can export using varieties of different functions to then fit in spectralfitting.jl or into XSpec or whatever. And then once you're happy with all of that, or if you want to change anything, it's very, very simple to modify. Changing the space-time is a one-line change and everything will recompile accordingly. Changing the disk is a one-line change. So in this case, we could change it to processing disk as shown in this GIF. Changing the corona likewise is a one-line change, and then we can calculate all those products again. Our code is entirely open source on GitHub. You'll see the link at the end with an open invitation for collaboration. Even if this isn't your field, but you just sort of feel like playing about with it, we'd love to chat to you. And yeah, thank you very much.
Yes, thank you so much, Fergus. If anyone has any quick questions before we move on, feel free to post those in the chat or to raise your hand through the Zoom functionality. I actually have a quick question for you, Fergus.
Yeah.
And this is something I think has been talked about a little bit in our past meetings. Can you explain why you chose to use Julia for this program instead of Python? The automatic differentiation is sort of like the main crux of what our code is using in order to get to benefit from a lot of the sort of simplicity and extensibility that we're relying on. And that is much easier to do in Julia than in any other language that I've encountered so far. In addition to that, Julia makes it very easy to make sure that your code is reproducible. So you get these sort of like full manifests and all that Python sometimes struggles with a little bit. Yeah, also the speed of it. You prototype in the same language that you're then doing the actual implementation in. So also the turnover of the development cycle is a lot faster too. Perfect, thank you. I think we have 2 raised hand questions that we'll do right now, and then any questions in the chat I'll save for the Q&A, if that's okay. Sam, if you'd like to ask your question.
Yeah, sure. Thank you. That's a great talk. I was wondering, does this code have the ability to just read in a metric from like an HDF5 file?
No, that is something that we really want to do, but I haven't been able to get any of the like numerical relativity simulators running yet. I haven't tried it too much, but that is something that we'd really like to do.
Okay, great. Thank you.
And Neil, if you had a question.
Thank you. This was like a very powerful tool. Love it. My question was, have you tried using any neutron star metrics like Hartree-Thorne? Does the code accept neutron star metrics as well, or is it just for black holes?
Sorry, say that again. Is neutron star metrics?
Yes. Can the code accept neutron star metrics as well?
Yeah, you could. So if I just go back here, when you're defining your metrics, you just subtype a specific type of metric, which just is related to the symmetry because it allows us to exploit some other sort of like accelerations. But then after that, you can do anything you like with your metric, even have, so you could in theory call out to like a pre-rendered metric on a grid or something like that here. We have got, no, we don't have any neutron star metrics in the catalog at the moment, but we have got like wormholes and things like that in there too.
Okay,
but yeah, you could add it. Thank you.
Thank you.
I'm realizing we did have one quick question in the chat. Fazal asks, can we work on single photon paths with this?
Yeah, very straightforwardly. So effectively, there's one function that it exports called trace geodesics, which can accept a variety of different input parameters. And if you give it just a single position and a single initial velocity, it will trace just a single photon and give you the full path back.
Very cool. Thank you very much, Fergus.
Thank you.
Any further questions we'll save for the Q&A at the end. And for now, we will move on to Hui Yang. Hui is a student at the George Washington University, and he is going to present to us today about multi-wavelength machine learning classification with MUWCLASS. Hui is also a 6th-year PhD student and will be on the job market next year.
Okay, can you see my slides?
We see your presenter's notes.
Screen.
However you were doing it. Perfect. There's your
Okay. Okay, thanks. Hello, everyone. My name is Hui Yang, a graduate student from the George Washington University, and I will be on the job market soon, and please stay tuned. So in this talk, I will present a machine learning classification pipeline for classifying X-ray sources using multi-wavelength properties, MUWCLASS, that we developed in the past few years. And this is also an important part of my thesis. Moving forward. So the X-ray astrophysics has entered a big data era thanks to the successful observatories like Chandra, XMM, and EuroSida. However, most of the sources detected are serendipitous sources with their nature unidentified, and this table shows the number of unclassified sources can be as high as millions. So one of the solutions to develop an automatic way to classify the astronomical sources using machine learning methods, which can enable efficient classifications and to reveal dependencies in large data sets with high dimensionalities. So we have recently published our paper on classifying a good fraction of Chandra source catalog version 2.0 sources with some quality card using our multi-wavelength machine learning pipeline MUWCLASS. So we used a supervised machine learning method where we rely on a training data set with well-verified sources that we built from literatures and online resources. It is consisted of 8 classes of X-ray sources with a total number of 3,000 sources. We have extracted X-ray properties from Chandra source catalog, and the sub-arcsecond localization of the X-ray sources enable us to cross-correlate with multi-wavelength catalogs, including Gaia, 2MASS, and WISE. And together we have up to 30 features used for the pipeline. And here on the right panel shows the importance of the about 30 features that we used. And these slides show the workflow chart of the pipeline, where we also take into account feature measurement uncertainties using Monte Carlo simulations and the extinction absorption biases for the AGNs, since most of the AGNs from our away from the galaxy plane, which make them look very different from an unclassified AGN in the plane. The whole pipeline is compiled in Python, where most of the machine learning algorithms are already available in the communities. All the classification results have been available online with table format. We have also made a demo code where the users can try to classify a small area of the sky that you are interested in with more details. Here, I would like to show the demo that we make. Can you see the slides with
We can see your Jupyter notebook.
Okay, that's what I'm so this is a GitHub repository, and you can so we have so to run, in order to run our pipeline, you have to install some packages. So there are 2 versions. One is a simple version where you don't have to install CHAL, which is a software you use to run the Chandra data analysis, or you can install a more complete version with installing the CHAL. So here I will show this demo where you have to install the complete version by installing the CHAL. And so so to run this pipeline, you have to load some packages, and then you have to specify a region of interest where you have to give the field of the name of the field and the RA and DEC and the radius. And you have to ensure that the field has X-ray sources that from the Chandra source catalog. Otherwise, because our pipeline is based on the Chandra source catalog, so the X-ray sources from the Chandra source catalog should be are required. Then it will extract the properties from the Chandra source catalog automatically and do the cross matching to multiple catalog, including Gaia, 2MASS, and multiple WISE catalogs. Then it will run the classifications using the random forest algorithm. But this is a default model that we use, but you can also change to some other supervised machine learning algorithms if you want. And the whole pipeline takes, the notebook takes a few minutes to run. And in the end, we will have the classifications. This shows the classifications of the breakdown of the classifications for the sources that we classify from these NGC 3532 fields, which is a middle-age open cluster that we're interested in. And this shows the broadband spectrum of the training data sources overlapped with unclassified sources that we classified in Cyan. And you can see the distribution of the classified sources is consistent with the sources from the training data for the broadband spectrum, which covers from optical, infrared, and up to X-rays. And here are some visualization of the some images from the different optical surveys. And in the end, this plot shows our classification results with the X-ray images. And you can, but we also can filter out those sources that are not confident classified. And here it shows all the sources that are confident classified in this NGC 3532 field with these X-ray images. And you can see many of them are classified as low mass stars in these orange stars, and some we did classify confident neutron stars, and in this magenta triangle. While we are developing this machine learning pipeline, we also developed some other tools that help to visualize our training data set. So this is a two-dimensional interactive plot tool that we developed to visualize our training data set. So so for different colors shows that for the different types of X-ray sources in our training data set. And so this you can also change to some different features that you want to show. Here is the plot of the Gaia BP MAC versus the X-ray broadband fluxes for the training data set. And you can also try to import the sources that we just classified from these NGC 3532 fields, which are plotted with these black circles. So the colors also shows the classification type that they are classified. So you can see that as we just showed, we have many stars that are classified, which are shown here in the orange dots. So they are consistent with the orange dots without the black circles that from the training data set. So this website is made with this CID view tool that is developed by another colleague from our group, that you can actually try to make a similar website using any table data that you have. So with this table, with this tool, we can also make a interactive visual tool for a Fermi source catalog. And so this is the application of this CID view that we use to make this visualization for our training data set that we use for our MUWCLASS classification pipeline. And in the end, I would like to show the GitHub repository for our machine learning pipeline, and this interactive plotting tool for the Chandra source catalog training data that we use, and this CID view, which is a Python code that we can make an interactive website for any CSV file with multidimensional numerical data. And that's it. Thanks.
Thank you very much, Hui. So we'll start and spend a few minutes just giving a short Q&A to Hui before opening it up to ask questions to any of our speakers. I don't see any questions in the chat right now, but if anyone either would like to post them there or use the hand raise feature on Zoom, we can also take a second to give it up for all three of our speakers. Thank you all so much.
Yay. I have a question for Hui.
Okay.
Yeah. I'm wondering if they're looking for any help in further developing the software, and if so, how could people engage with the project?
Yes, so currently we only have a pipeline for the Chandra source catalog, but we are also planning to do it for other X-ray catalog like XMM, or if Erosita publish their catalog, if you want to join us, you can send us an email and we can try to collaborate. I think that's or you can try to join the GitHub repository and try to make any requests, and we can improve or we can collaborate from the GitHub as well.
Okay, so if somebody wanted to help out, they could file an issue perhaps, or address one of the issues that you already have.
Yeah.
Yeah. Okay, great. Thank you.
Thanks.
So in the Jupyter notebook you were showing, there was one part though where it was referencing several other catalogs, including the 2MASS catalog. Can you explain again what that was? I was curious about that.
Because we are using not only the change source catalog, because this is multi-wavelength properties that we want to use. We also cross-match to other catalog, including optical from Gaia and infrared from 2MASS and WISE, which we use AstroQuery to do the cross-matching. Yeah.
Okay. That was going to be my question, is I was curious how you were doing the cross-matching there. So
yeah.
Thank you.
Yeah. And we're also trying to implement some new methods like N-way to do like probabilistic cross-matching in our like next work. Yeah.
Okay. Interesting. Thank you.
Thanks.
So yes, if anyone has questions for any of our three phenomenal speakers here, feel free to either send them in chat or to use the hand raise feature at any time. Alice doesn't even need to use the feature. What? Yes, Alice, go ahead.
Well, that is the hand raise feature.
Exactly.
So I have a question for M. Has your software been used in any refereed research?
No, not currently. So we're presenting Fedanka as a major component of a current paper that we're getting ready to submit. So that will hopefully be submitted sometime in the the next week or two.
Ooh, okay. We should talk. And let's see. I had a question for Fergus. Actually, I have the same question for Fergus. Has Gradus been used in refereed research?
Not yet. We're currently working on our sort of like announcement paper, I suppose.
Right. Okay. And we has already shown that his has been used. So I don't have to ask that question of him.
Actually, because for my pipeline, I don't like it can be used that easily because all of the classification results have been published. But right. The notebook that I just showed is if you are interested in some specific field, you can try to understand this machine learning pipeline by digging into this notebook and try to understand how it looks. Yeah, I think because I feel like my pipeline is kind of not fitting into the software, but we are also trying to look some other ways that people can use it like more. Yeah.
Okay.
Thank you. Oh, sorry, Alice.
No.
I had another question for you, Emily. As you already know, and for everyone else's reference, I've done some work with isochrone fitting before. I was curious about the dynamic time warping algorithm you mentioned. Would you maybe in layman's terms be able to explain how that works? You said it was originally developed for sound data. Yeah,
so this is an algorithm which, like I said, it was originally developed for, I think, synchronization of like microphones from onboard cameras and external microphones or similar problems. The gist of it is it's looking for shared features, and it is theoretically invariant to linear transformations in the data, including compressions. So the underlying math that it's doing involves basically taking derivatives and doing convolutions of kind of higher order derivatives and looking for shared features in those. The benefit of this is it's very good at identifying shared kind of shared scale points. What the MESA group would call, right, and I think other groups would call equivalent evolutionary points. If we think about applying this to kind of co-evolved populations, it tends to be an extremely slow algorithm. There's a major kind of performance impact of doing all these higher order derivatives. However, so what we're actually implementing is something called a fast DTW algorithm, which is marginally different. It doesn't necessarily give you the provably best what's called path, the basically kind of correlation between the two signals. But it does do a very good job of giving you an approximate correlation, and from there we use that basically as a limiter in our objective optimization. So then we just have a much more limited space to explore, and then we explore it's kind of like a more standard gradient descent, or if you want to be a little more formal, you can use like a dual annealing method.
Thank you. Very interesting. Hui has his hand up. I'm not sure.
Yeah, I have a question for Emily because I don't know this isochrone fitting that well. Like for an open globular cluster, there might be some background or foreground sources. Does your fitting can help to distinguish those sources? Yeah.
So it's a good question. That's not something that we've specifically built in. So kind of our pipeline or our software, assumes you're working from a database of stars within a cluster. So, we've been working a lot with the ACS database and the HUG database for Milky Way globular clusters. In terms of, if you had something that wasn't necessarily as filtered as those are, you could look at, is a star not necessarily, within some distance of the median ridge line, but there are other issues there. Stars can, binaries are going to push stars around, or like blue stragglers are going to push them around. So I don't think that necessarily like purely a measurement of the fiducial line would be a particularly good indicator of cluster membership or not.
Thanks.
Thank you. We have a question in the chat. Again from Neil. He says, Fergus, do you think it would be easy to adapt the code to dynamic spacetimes, such as around a binary merger?
Yeah, it's something that we are sort of considering to do, but haven't done yet. But we've been developing the library very much with the idea that everything could be dynamic in some sense. So yeah, again, when you're defining your metric, you can make those different metric components dependent on the time as well. In which case you can, change what's happening with your space-time so you could also then have, like the slow light and the fast light approximation. So the idea is the space-time is evolving as you're tracing the trajectory, or that you have some sort of evolved time step and then you trace different images at different time steps afterwards. So you can do it.
That is very cool. I, as a current master's student, what I found so interesting about yours is how you're visualizing everything, because you take GR courses and it's just everything is just lines and lines of math, and it's easy to lose that physical intuition. So that's certainly something I appreciated about that. We have a hand raised here. Would you like to unmute and ask your question?
Yeah, sure. This is a question for Fergus. So I do ray tracing as well. So I'm just curious. So are you tracing the rays forward from the source, or from the image plane, or backward in time?
It depends on the context. So for the image planes, we're doing it from the image plane backwards, and then sort of doing the time reversal. For things like from the coronal sources to the disk or whatnot, then that would be forward in time. Yeah.
And so do you have like ray objects, or how do you do each trajectory? Can you modify, say, do multiple reflections, say, of any order?
Yeah, so we at the moment everything's kind of defined in terms of like integration charts, which is just basically where the integration stops and ends. So if you had a piece of geometry that you wanted to put reflection into, you would have you would integrate your trajectory until you've intersected with that piece of geometry, and then from the endpoint from there, use that to initialize your new trajectory, and then fire off another geodesic with that, which would be your reflection. But we don't have anything that's automatically doing that at the moment.
Okay, but can you do diffuse reflection? So could you have one photon splitting into many?
Yeah, so this kind of also builds into a little bit like the Monte Carlo radiative transfer stuff that we're kind of looking to extend into our code, so that there's a full API for it as well. At the moment, you can do it, but it would be, work from your perspective, as opposed to like the library manifestly does it.
Okay, so I'm interested in the paper when it's out.
Thank you.
Great. Do we have any more questions for our speakers here? We had a speaker drop out at the last moment, so we might just have to close up a little early today, but I certainly don't want anyone to leave with any lingering questions.
I want to say that Wei's cat looks awfully comfortable where he
Yes,
is.
yes.
So
He,
it looks like he owns that desk.
Yeah, he like to help with the research. Mm.
You don't need a rubber duck. You can just speak to your cat. Okay. Have you ever heard of rubber duck decoding, Alice?
No.
It's so the idea is you have a rubber duck on your desk, and when your code's not working, you explain what it's supposed to do to your rubber duck, and you
okay.
walk it through, and it's
Okay, well, I usually refer to the rubber ducks that I have done that to as people. So like the guy down the hall who like had no idea what I was talking about, but would nod in the right places.
Oh, that works just as well.
And I would talk through, and then I'd thank him. I'd say, "Oh, okay, now I know what I need to do. Thank you so much." And he'd be like, "Okay." So
oh, thank you, Orlando. There's a
Yes.
Wikipedia article for you. Okay, well, if there are no more questions for our speakers today, I want to take a second to give them all one last round of applause. Thank you so much for coming. Is that Jordy that you're holding? Can we see her? Yes. Jordy.
Yes,
Thank you all so
so-
much for coming today.
yeah, so the tradition is at the end, if you have any pets and you'd like to show them, we would like to see them.
Yes.
So,
Yes. Thank you to everyone for coming today. And as a quick heads up, next month on July 19th, we are going to be doing a session on teaching computational astrophysics. So we hope to see everyone there for that. Yes. Thank you very much for coming.